Module 9 review. Okay, so we're looking at Chapter 11, and these are the sections covered in Chapter 11. Note that Chapter 11.5, so section 11.5, we will not cover this section in this course, but we will all of the others. Today we're going to focus on section 11.2, the one-way ANOVA for the completely randomized design. And if you understand it well, then the randomized block design in section 11.4 should fall into place quite well. So we're going to focus on the one-way ANOVA today and also the multiple comparisons test. All right, starting with a life expectancy example, we have here, we're seeing the first 7 countries, but they go on to 193 countries in this data set. And so for every country, we have recorded the average life expectancy and the corresponding continent to which that country belongs. And there are a total of 6 continents: Africa, Asia, Oceania, Europe, North America, and South America. And so what I have done is I have taken the average life expectancy for all the countries in Africa, Asia, Oceania, Europe, North America, and South America, and calculated it into a table right here. So this is X bar for each of the continents. So we have 6 continents here. And there, so for example, Africa life expectancy is 57.54 with a standard deviation of 7.96. And the N is the number of countries. So N subscript I says 52 countries in Africa for this data set. Asia has 50 countries. Europe has 42 countries, 13 Oceania, 25 for North America. It's where we are. The 3 main ones is, of course, Canada, US, and Mexico. But there's also Cuba, Dominican Republic, Antigua, and so forth in North America. And then there are 11 countries in South America. And those are the average life expectancies for each of those continents. So we can look also at the box plots for each of these continents, compare the differences in their averages. And so if you remember way back, box plots, these are the distributions. So for Africa, there was 52 countries, Asia 50. There's an outlier, another outlier, another outlier. And we can go, well, are they different just by chance variation, just the random variability in the data? Or are they statistically significantly different? And we can look at their means that I've calculated and we can wonder if it's just chance variability or not. And remember, the center line for each of these box plots is the median, but we can still see visually that there is a difference. But is it just due to chance, or are they statistically significantly different? Right. So that's the life expectancy along the vertical axis for each of the continents along the horizontal axis. So what can we do? Well, we could compare each possible pair using difference in means t-tests. We could run a t-test for each pair. And because there are 6 continents, choose 2, that would be equal to 15 pairs. So we would have to compare the means of each and have 15 t-tests at, let's say, alpha equals 0.05 level. But there's a problem. The problem is that each hypothesis test comes with a probability of a type 1 error equal to the significance level alpha 0.05 in this case. So what is the probability of a type 1 error if we test all pairwise combinations of means? Well, the probability that none of those tests, none of them having a type 1 error, is equal to 0.95 to the exponent 15, right? Because that would be 15 t-tests. And then the probability then of at least one of those tests have, at least one of those tests has, I should say, has a type 1 error would be then equal to 1 subtract 0.95 to the exponent 15, which is about 0.54 or 54%, which is quite high. So the probability is quite high if we were to compare and run 15 t-tests to see if there's differences, any statistically significant differences in the population means. And so we can see, though, as the number of groups or the number of continents increase, that probability of at least one type error also increases. So that would increase the 54%. So what we can do instead is run a global test, an ANOVA. And we can use a one-way ANOVA. It's stands for analysis of variance. And this type of test is frequently used in psychology, epidemiology, and other fields that rely on experiments. We call it a one-way because we are exploring one characteristic, that is life expectancy. We could explore two characteristics, have a two-way ANOVA if we had life expectancy and weight, let's say, but that is more complicated. Here, if we use a one-way ANOVA, we can use it as a global test. Instead of running 15 t-tests, we could have one global test where the null hypothesis is that the population means are all equal. Here is the null hypothesis. For this ANOVA test, we have 6 continents. So the mean of Africa is equal to the mean of Asia, is equal to the mean of Oceania, and so forth. All 6 continents are equal. And then we can test that against the alternative hypothesis, where at least 2 of the population means are unequal, which means another way of saying that is one of the population means is different from the others, from one of the others, at least one of the others. So note that this can be all population means are different. It might mean some of the population means are different, maybe 3 or 4 or 5, or just that 2 are different. And so there's no way of knowing if we reject the null hypothesis and accept the alternative, we don't know whether it's all the population means some or just 2. So then we can move and go forward from there and do what is called a multiple comparisons test, which we will see later. But first, the ANOVA, we can conduct the test, and how we do this is we compare the between group and the within group variation. And the total variation is comprised of these 2 sources of variability. One is the variability between the groups. For example, we can compare the mean life expectancy for each continent to the global mean life expectancy. The global mean is also called the grand mean or the overall mean. So that would be the mean of all the countries, 193 countries. And so we could compare the mean life expectancy for each continent to that global mean life expectancy. 2 is we could also do the variability within groups, and that would be, for example, compare the life expectancy of individual countries to their continent's mean life expectancy. So we have 2 sources of variation between the groups and within the groups. And when you add them together, we get the total variability. And how do we calculate those variabilities? We have our sources of variation. So this would be the between the groups, or treatments, between the treatments or the groups. And the error is also within. So within the variability within the groups, we also call that the error. C is the number of groups. In our case, we have 6 continents, so that's C would be 6. N is the total number of observations. And in our case, we have 193 countries, so that would be our N. Then we calculate what is called the sum of squares. So the variation is calculated for the between the groups is SSC. Think of C standing for columns. So you can arrange your data in where your groups are in columns. So the SS, sum of the squares for the columns, is from the sum of I equals 1 to C, and where N is the size of the sample for each of those groups. And then the mean for each group, X bar subscript I, subtract there's our global mean or the grand mean or overall. And then we can calculate also the within the error, within the groups or the error, SSE, E stands for error. And we have the sum from I equals 1 to C for the size of each group, right? So think of Africa, we had 52 countries, subtract 1, multiplied by the standard deviation squared, which is the sample variance. Okay, and both of those added up, SSC plus SSE, so the sum of the squares for the groups plus the sum of the squares for the error equals the total. The sum of the squares, T for total, which is the sum of each observation, subtract the global or grand mean squared. And each of these variabilities has have an associated degrees of freedom. So the degrees of freedom for the between is C minus 1. The degrees of freedom for the within variation is N subtract C. And then we have the total. So C subtract 1 for the between added to the N subtract C for the within has to equal N minus 1. Okay, so those first 2 rows add up to the third row. And that is our ANOVA table. We call this an ANOVA table, and it can get extended. You'll see how it gets extended in just a moment. So we have our life expectancy example. The SSC is the sum from I equals 1 to 6 continents. And each continent has a number of countries, N subscript I, their mean, subtract the global mean. And so we need to know what the global mean is. So if we take each continent's average and add them up, so the first one was Africa, 57.54, and we add up all the way up to South America. South America was 73.81, and we get a global mean of 71.51667. I'm going to carry that many digits. Okay, so we can plug these in now. So the first one is Africa. That's going to be 57.54. Subtract 71.51667 and squared. We want to square those. Next, Asia, 50 countries with 72.02. Subtract 71.51667 squared. Next, we want 42 countries, 78.11, subtract 71.51667 squared. Next country, 13 or continent, right? We're summing the continents here. That's going to be 72.69, I believe. Subtract 71.51667 squared. Next, we have North America, 25 countries, 74.93. subtract 71.51667 squared. And finally, we have South America, 73.89, or sorry, 73.81. Want to be careful there. I don't make a mistake. So 73.81. Subtract the overall mean. And we get, that all ends up being 12,363.57. So that is our SSC, sum of the squares for the groups. And in this case, our groups are continents. Sum of the squares for the error or within the groups is the sum from I equals 1 to 6. You take the size of each continent, the number of countries within each continent, subtract 1, multiply it by the variance. And that ends up equaling, so we'll put down here, first one is 52, subtract 1, that's for Africa, multiply by 7.97 squared. Asia, 50, subtract 1, multiply by 6.33 squared, plus 42, subtract 1, times 3.93. And this is all coming, by the way, this is all coming from the data on slide 4, right? All the data is coming, all of these values are coming from slide 4. Plus 13, subtract 1, times 5.37 squared, and that's 42, 13, now 25, subtract 1, times 4.13 squared, plus 11, subtract 1, times 3.26 squared. All right, so if you go to slide 4, you can cross-reference this to see that it's all been entered, written down accurately. Just going to do a quick check. I believe that is right. Okay, and that ends up being 6,697.87. All right, we can now calculate the SST, which equals the SSC added to the SSE. So the sum of the squares for the total is comprises of those two sources of variation, the variation between the groups and the variation within the groups. And the total is I'm going to change this to approximately 19,061.44. So all of the calculations have been made. We can now enter these into an ANOVA table that has been extended beyond the sum of the squares and the degrees of freedom. So we can do this. We can have our source. We can have our sum of the squares. We have our degrees of freedom, and we'll have our MS. We'll leave the F value for another slide. Sum of the squares, degrees of freedom. So we have between that we've calculated. We calculated the within, and we also have the total. So the sum of the squares for between, we calculated at 12,363.57. For the within, 6,697.87. And the total, you add those two up, and we got 19,061.44. The degrees of freedom. So we have C equals 6 continents. N equals 193 countries. From that, we can figure out the associated degrees of freedom with each of the sum of the squares. And we need that because we can then calculate the MS column, which is the mean squares. So we have the sum of the squares, and then we have the mean squares. So C subtract 1, that'll be 6, subtract 1 will be 5. And then N subtract C, 193 subtract 6 will be 187. And then n subtract 1, we have 193 countries, subtract 1, that'll be 192. Again, the sum of the degrees of freedom for the between plus the within, so 5 plus 187 equals 192. And then it's correct. And then for the MSC, that's going to equal the sum of the squares for the between divided by the degrees of freedom for the between. And the MSE is going to equal the sum of the squares for the error divided by the degrees of freedom associated with the error. And that's why we put this in a table, so that it's easy to keep track, because we're using all the values as we go from left to right to finally get the F value. Then we can run the test. So we have our table and the F value. So we call this the F statistic. There we go. It all disappeared. Now it appeared. The ANOVA F test. So F stands for Fisher, the statistician that developed this test. And the F distribution is, we've used the tables before from previous content in the course. It is the ratio of two chi-square random variables on n degrees of freedom. And for the ANOVA test, that is going to, one, I can go even further. This is going to be, let's do this. It's going to be the sum of the squares for the treatments divided by the degrees of freedom for the treatments divided by the sum of the squares of the error divided by the degrees of freedom for the error, which equals the MSC, the mean square for the groups, divided by the mean square error. All right. And what it does is, what we're doing when we have this ratio is we're comparing the between group variance, which is the numerator, to the within group variance, which is the denominator. If there is a large difference between the two, then we have reason to reject the null hypothesis. Why? It's because this suggests the mean between the groups differ. It's different. They're different. If it's small, so if the ratio is small or no, so no difference would be the ratio equals 1. So MSC divided by MSE equals 1. That would be no difference, right? They would be exactly the same if you divide them. So that, or small difference between the two, right? Between the group variant, the between group variance and the within group variance, the numerator and the denominator, then we have less reason to reject the null. And why? It's because this suggests the mean between the group is not differing or not differing that much. Okay, if we look at our F, we had our sum of the squares for the between divided by the degrees of freedom for the between, the sum of the squares for the error or within divided by the degrees of freedom for the error or within equal the MS, so the mean square for the groups divided by the mean square for the error. And we ended up getting for this 2,472.71 divided by 35.82, right? And that's how we calculate that. So you take those values and divide, and we end up getting 69.03. Okay, so I hope everyone's clear. The MSC was in the numerator is composed of 12,363.57 divided by the degrees of freedom, which is 5. And the MSE in the denominator is calculated by taking the sum of the squares for within, which was 6,697.87 divided by the degrees of freedom, 187. So that's how we get that. And we now need the critical value. So that's the observed value for F. We need now the critical value for F from the table. So let's use alpha of 0.05 and 5 degrees of freedom for the groups and 187 degrees of freedom for the error. That's because our table doesn't go up to 187 degrees of freedom. We're going to use alpha 0.05, 5, and we're going to use 120, which is the maximum degrees of freedom for the denominator. It'll be close enough. And we'll go to there. All right, we want the F tables. So this is the F table. So we want alpha equals 0.05. Here it is here. All right, and we want 5 degrees of freedom in the numerator, right, for the mean square for the groups. And then we want the denominator. Now, 187 would be somewhere around here, but you can see we're going to use 120. And if you look at the value between those two, it comes to 2.29. So we know that if 87, the maximum here, we have infinity is 2.21. So 187 degrees of freedom would be somewhere between 120 and infinity, which means the value for the F would be somewhere between 2.21 and 2.29. So it's close enough. It's going to be very close. 2.29 is fine to use. And now what we want to do is ask ourselves, is the observed F greater than the critical value F? Because if you look at the distribution, our critical value F corresponded to 5% under the curve, the area under the curve. F star equals 2.29. So is our observed value in that critical region, is it in the rejection region, right? Is it there? So, and the answer is yes, right? Because 69.03 is greater than 2.29. And even if you just look at the ratio, before you even calculate the 69.09, if you look at the numerator, 2,472.72 is quite different than the denominator, 35.82. Like already there, it looks like the between group error is greater, much greater than the within group error, right? So the between group is much different than the within group. Therefore, we reject the null hypothesis. And that means that we accept the alternative hypothesis and we state that there is a difference in life expectancy in means for at least 2 of the population means, right? The alternative hypothesis means that at least 2 of the means are different. Could be all 6 continents averages are different, statistically significantly different, or maybe 2 or maybe 3 of the continents, 4, we don't know. We just know that at least 2 are unequal, right? And that is the one-way ANOVA F statistic.